guys, this is Miss Nickel, and I am making this video to go along with the Molecules to Moles practice quiz that was posted for April 13th through 17 in Google Classroom. So I know it's been a while since we've done some of these things. I'm not going to go over counting the number of atoms of each element in the compounds right here at the top, because I have a separate video on this that is also posted in Google Classroom. So we're going to go on down here where it says remember molar mass. I know, it seems like a bad dream coming back again, doesn't it? Molar mass, what is that? We can hardly remember, but it's all going to come back to you, I promise. So a mole was that constant number, right? 6.02 times 10 to the 23rd atoms. So I'm going to write that down right here. That's Avogadro's number, 6.02 times 10 to the 23rd atoms in a mole. Now, that's just what the definition of a mole is. You don't have to know that to do these calculations. What you have to know is the mole is giving us a constant number of atoms, but depending on the element we're talking about, that mole, that number of atoms will weigh a different amount, because atoms have different sizes, right? Depending on how many protons and neutrons they have, that's going to change the size of the individual atoms. So if you have bigger atoms, they're going to weigh more. So aluminum here, this is what we call our atomic mass down here at the bottom, and it also gives us the molar mass when we convert it to grams. So when we look at this and we say, what is the molar mass? We just take this number, we round it to the nearest whole number, and we say that's the molar mass. So in the case of aluminum, that would be 27 grams per mole. That's how much 1 mole of aluminum weighs. So this is not the same elements and examples that you have in your test. I made a different copy of the test so that I could go through this with examples, and you can still complete your practice tests on your own. So how do I find molar mass of these different elements here? Well, I'm just going to go to my periodic table, of course, right? And so I think the first one I had here was silver. I'll find silver right here. And you can see the molar mass of silver is 107.87. That's grams per mole. I'm going to round it to 108. So that is going to be 108 grams per mole for silver. Now I'm looking at bromine right here. 79.9. I'm going to round that to 80. Anything that is 5 or greater is going to round up. So that's going to be 80 grams per mole for bromine. I'm looking at neon. I just happen to know where that is. I think it will take you guys a little longer. You're going to have to dig out that periodic table, or I think I'll just go ahead and have one posted in Google Classroom for you. So neon, we can see that's going to round down to 20, right? We're looking at the 10th place to round. So that was going to be 20 grams per mole. And our last one here, rubidium, is over on this side of the periodic table right here. That is going to be, well, it's just on the edge there, but it's going to stay at 85. So 85 grams per mole for rubidium. Okay, so that's how we find it for individual elements, but we are going to be interested in doing this for compounds. This skill, we're going to combine this with how we balance equations, and we're going to be able to figure out if we start with a certain amount of mass, how many moles we have, or if we have a certain number of moles of a chemical reactant or product, what mass we should expect at the end of the reaction. So that's why we're learning about this again. So the compound we're looking at here is called lithium fluoride. This is really similar to what you have on your worksheet. And so to find the molar mass of a compound, I'm just going to find the mass of the elements, multiply them by the number of times that element occurs in the compound. That would be the subscript, and then multiply it by the number of atoms in the compound, okay? So here I just look up molar masses of lithium and fluorine. right? So if you have a capital combined with a small letter, that's a single element here. Lithium is one element and fluorine is the other, okay? So here we're looking at lithium over here in the periodic table, and that has a molar mass of about 7. So I'm going to call that 7 grams per mole. And my fluorine over here has a molar mass of 19. Grams per mole. And we have to look at the number of atoms in the compound. Well, because there is no subscript for lithium or fluorine, that's going to be 1 for both of these. So we really don't have to do much there, do we? But if we did have multiple atoms, had a subscript other than 1, we would multiply by that number here. We go straight across. So that's going to be a total of 7 grams. Because this is telling us we could call this also number of moles. So we're just going to change it to grams at this point. So 7 grams and 19 grams. And then we're going to add that together for a total of 26 grams per mole. Yeah, and I guess we will just, for now, we'll be talking more about some things like this, but we're just going to keep it as grams per mole here too. So that'll be a total of 26 grams per mole for lithium fluoride. All right, so let's look at another example here on my sheet is a situation where we have a polyatomic ion. So you should know how to do these. This is why we've been working on counting atoms. You guys should be getting really good at this. And I'd be looking up my individual molar masses of those compounds. So I'm not going to show you those this time, but it's just going to be 40 grams per mole for calcium, because I have 1 calcium, and I'm just going to list the amount for 1 atom right now. So oxygen is going to be 16 grams per mole, and hydrogen is 1 gram per mole. Now, I have to figure out how many atoms I have of each of these. I only have 1 atom of calcium, but because hydroxide is being treated like a polyatomic ion here, and hydroxide ion is an OH together, and this subscript here tells me that I have 2 of these. So I have 2 of everything inside the parentheses. That means I have to multiply the oxygen by 2 and the hydrogen by 2. Okay, so individual atom subscripts only apply to that atom, but subscripts that are on the outside of the parentheses apply to everything inside. So now I have my numbers down. I'm going to multiply across. So it's going to be 40 grams per mole and 32 grams per mole and 2 grams per mole. Just like that. I'm going to add those up, and we're going to get 74 grams per mole for that compound. Okay, so now let's talk a little bit about balancing reactions again. So when I'm asking you what kind of reaction this is, you had a video about synthesis and decomposition reactions. And we also took some notes on these right before we had our break and the quarantine situation. So I have this posted in the Google Classroom also, and it's what was supposed to end up in your notes, but I know a lot of you didn't get that done. And we had a slide presentation on it, but it's all summarized here. So these are the different reaction types. The video talked about synthesis, where 2 things come together and make a single molecule or compound, and then decomposition, where a single molecule or compound breaks down into 2 separate elements or compounds. Then we have our single and double replacement reactions. Now, I haven't talked about those with you so far, but those are really pretty straightforward, and you'll be having an assignment about those next week. The basic idea is kind of like as if you had dance partners, and this is how it works. Say you have 2 people dancing together, that would be D, F here, and C comes along, and C is by herself, and so C kicks D out of the compound and becomes F's dance partner now, and D is by herself, okay? So that's, we just have one element being replaced by another element, and the element that isn't in the compound is by itself. Now, in the double replacement reaction, we have two dancing partners that swap partners. So G and H are dancing and J and K are dancing, and they decide they would rather dance with the other person's partner, so they just switch places, and now G dances with K and J dances with H. Okay, so pretty straightforward on those single and double replacement, and we'll talk more about combustion another time. Okay, so when it asks you kind of reaction, then you're going to have four choices: synthesis, decomposition, single replacement, and double replacement. So right here, this looks to me right away like this is going to be a synthesis reaction, right? I've got two things coming together to make a single compound. So I'm going to call that synthesis. And now I have to figure out how to balance this equation. And I like to do this part in pencil. So we're going to list the number of atoms of each compound. Some of you may have learned some other approaches, and that's fine, whatever works for you. I'm not going to grade you on the approach as long as you get the correct final answer. Okay, so I have aluminum, and here my chlorine is going to be equal to 2, right? Because we set it equals to its subscript. If there is no subscript, the subscript is automatically 1. And then here with aluminum chloride, it's going to be Al equal to 1, right? Because aluminum has no subscript, but chlorine, Cl, has a subscript of 3. So that's going to be equal to 3. So if I didn't know any better, I'd probably just come along here. I'd compare my aluminums. They look the same. And now I would compare my chlorines. But here I have a situation. I've got 2 on this side and 3 on this side. So if I just double either one of these, that's not going to fix the problem, right? That'd be the same as adding one more molecule of either one. But if I double this one, I'll have 6 of these chlorines, right? So say I put a 2 here, that would mean I have to multiply this aluminum by 2 and this chlorine by 2. That's going to be equal to 2 and equal to 6, just like that. Now, let me see. If I have 6 of these, how many times would I have to multiply this chlorine to also have 6? 3 times, right? So that's going to be times 3, and then that will equal 6. I'm going to circle my finals for each of these compounds, and wait, I just noticed a problem. My aluminums are not the same. I'm going to have to add a 2 in here, and that's why I balance things in pencil, because sometimes I get ahead of myself. So there I go, times 2 equals 2, and now my equation is balanced. You guys can check me on that. Okay, same number of atoms of each element on either side. I can never change the subscript. I'm going to start on the left with the first element that I come to, compare it to the other side, and add to the side that has less, usually. Although here you'll notice that the 3 was actually a little bit greater, and I could have gone back and forth, but you get an instinct in these 3-2 situations that you're going to have to end up with 6 of each atom on both sides in order for the equation to be able to balance. So if you see a 3-2 like that, you'll just know to multiply by whichever numbers are going to give you 6, and then I make my final adjustments. Okay, so this was for our other problem. Kind of reaction here. So I have one dance partner swapping places with another dance partner, and now this partner is on their own. So I'm going to call this a single replacement reaction. I'm going to set each of my elements in the compounds equal to their subscript. Okay, I'm going to start on the left and compare. My sodiums are the same. I don't need to change anything yet. My aluminums are the same. I don't need to change anything yet. My chlorines are not. I have 3 here and only 1 here. So I'm going to add a 3 coefficient to this side. That will give me 3 chlorines, right? But I also have to multiply everything in the compound by 3. So I have to multiply the sodium by 3 as well, and that's going to give me 3 sodium. So I'm going to have to go back then and make an adjustment over here. I'm going to add a 3 in front of sodium. That'll be a times 3 there. So now my sodiums are balanced, my chlorines are balanced, and it looks like my aluminums are balanced. I'm going to go ahead and put in my finals for each of these. It just kind of helps me do that final check at the end to make sure I haven't overlooked anything.